It's there. I think JD, you can start.
Just 1 second.
It has not started actually.
It says custom live. At least I see that.
Custom live is there. Okay.
Yeah, it's there.
It is there. It is there.
You can
now it is.
Yeah, you can start.
Okay. Okay, we are going to start now. So first of all, I welcome all of you through the YouTube live channel, as well as the Zoom medium through which we are actually beaming this particular session of the joint IISc TIFR webinar series in chemical sciences. So I am Jyotishman Dasgupta and my colleague Professor Satish Patil from Indian Institute of Science, Bangalore. We jointly host these sessions once a month and 2 lectures at a time. And this has been a fascinating series for both of us to host, because we have gotten to know so many fantastic subject experts who have come here and given talks and illuminated many of us in India, both the students of the institutions, both the institutions, TIFR and Indian Institute of Science, as well as other institutions who have joined into this seminar series. So we are very thankful. We are very thankful we are able to host this series. So one of the principal motivations behind this series has been that world-renowned experts could come and sort of illuminate the fundamentals of a particular topic, a subtopic in chemistry, and not only illuminate the issues associated with that topic in a pedagogical way, but also talk about the research forefronts associated with the topic. And we have had fascinating discussions from all ranges of chemical sciences subfields. But today we are going to look at intramolecular vibrational relaxation as a problem in complex molecules. And we have a fantastic world-renowned expert, Professor K. Srihari, joining us from IIT Kanpur. So I just wanted to, before Professor Satish Patil, my colleague, introduces Professor Srihari, I would like to thank the American Chemical Society, ACS, for being a part of this series and encouraged us to ensure that we can host speakers from around the world using the Zoom platform. So they funded us for the Zoom platform. And we really would like to thank Diksha Gupta and Ajay Jha for doing this for us. Satish, you can now formally introduce.
Yeah, okay. Thank you, JD. Let me begin by welcoming you all for this IISc TIFR webinar series. Indeed, it's a great honor and privilege to introduce today's speaker, Professor K. Srihari. Professor Srihari did his undergraduate studies, BSc in chemistry from Vivekananda College, affiliated to University of Madras. Then he moved to state for his master's in chemistry in Bologna University. He obtained his master's degree in chemistry in 1987. Subsequently, he moved to University of California at Berkeley and obtained his PhD in 1989 to 1994. He worked with a very famous quantum chemist, Professor Bill Miller, at UC Berkeley, and then subsequently he did his postdoctoral studies at Cornell University in 1995 to 1996. So he joined IIT Kanpur as a in 1997 as a professor of chemistry. So his research interest is around chemical reaction dynamics, mechanism of intramolecular vibration energy flow, dynamical tunneling, and fundamental problems which what they address with the classical and semi-classical quantum dynamics. So of course, Srihari has received many academic awards and honors. He has been received this INSA Teaching Award in 2017, and he has been, invited to give a talk in Hokkaido University under this is Ambitious Leadership Program in 2016. He also got a Chemical Research Society of India CRSI bronze medal in 2016. So with this brief introduction, I invite Professor Srihari to deliver his lecture. Over to you.
Okay. Thank you, Satish, for the introduction, and thank you very much for keeping it short. So let me start by, I guess I should share my screen.
Yeah, share the screen. Yeah.
Okay. Let me share the screen now. So, okay, good. Right. So let me start off by first of all thanking Jyotishman and Satish, and I suppose the ACS as well, for this opportunity. It is actually a wonderful opportunity because it's a two-part series. So many times what happens is when one wants to really get into the depth of the research, one lecture doesn't cut it. And you know, it is actually not so easy. And therefore I was in some sense overjoyed when I got this invitation from Satish and Jyotishman. But the joy lived only for about a week or 10 days because of two reasons. One, when I saw the quality of lectures that were being delivered, I think the last one I saw was by Ned Seibert, who broke the record of the number of Zoom viewers who got in there. So a tough act to follow, as well as Professor Spano, actually, brilliant lectures. And I think these are the two, maybe I've attended one more, but all of them have been wonderful. So that is a lot of pressure on anybody who follows now. And this is not easy. Second thing, the reason I got overjoyed, but then the joy sort of faded off, is when I realized the enormity of the topic that I'm supposed to talk about. As you will see, this particular problem, perhaps even 2 lectures are not sufficient, really, because it's such a venerable, old, and yet highly relevant problem today. So feel free to stop me as I go along. I have, and as per JD's recommendation, I really have made sure that the first part of this is very pedagogical as far as possible, and I really get into the details of showing some derivations, for example, to see how things come along, and hopefully that will help students in particular. So with that, let me thank JD and Satish again for this invitation, and as I say, hopefully I will live up to the promise of the series. So okay, so let's get started. This is a beautiful problem. This is a fantastic problem. I've been working on it for nearly 25 years now, more. And the reason I chose this title, A Knotty Problem, is actually a very knotty title in some sense, but it's also very correct. As you will see, there are so many things that we still don't understand about this very fundamental phenomenon that is central to all of chemistry. And it's amazing, as you'll see, that it's been around. It's been around for more than a century. So what is it that we don't understand? Now, Ned actually gave a beautiful lecture which sort of introduced, so it made my job a little easier. So there are some things I'm going to repeat, hopefully slightly different from what Ned said. So perhaps it will build upon what was earlier mentioned in this context. But as Ned pointed out, this entire topic actually is very rich. And it has quantum mechanics, of course. I mean, that is the true chemical nature of molecules we have to worry about. It has classical mechanics, it has statistical mechanics, and it has various different angles, which are really fascinating. And in fact, we have, I must say that in fact, I should mention definitely Professor Sanjay Vatagaonkar's name and Professor Naresh Patwari's name, because in India, one of the earliest studies on IVR experimentally was by Sanjay and Naresh. And I have read that paper, but I haven't put it up because I haven't still completely understood it, Sanjay. Okay. So, but nevertheless, but I think there were a couple of papers. After that, they moved on to other things. So maybe that explains why it's a knotty problem, or maybe not. We'll see. We will wait for Sanjay's comments later on. this is a particular problem where I want to sort of bring out, first of all, the broad brushstrokes first, before I dive into the absolute details. So let's sort of start out. Yeah, and in fact, I should also mention, I mean, there is Jayashree, who worked with Ned, and Amber, who worked with Ned, although Amber didn't work within IVR. Sai Ramesh, who definitely worked on aspects of IVR. So yeah, it's wonderful to have them as well here, hopefully, listening to this. Okay, so why is it a knotty problem? So let's first get started with that. Okay, let me see if I can convince you. So the first point is that if you go back and search, and maybe this is not the oldest one, by the way. This is actually a paper written by G.N. Lewis and David Smith in 1925. So close to 100 years ago. And this actually is a very interesting paper, although Lewis got it wrong. But the point is, he makes a lot of very poignant points regarding this theory of reaction rate, which actually ties in very intimately with the phenomena of intramolecular energy flow. Look at what actually this said, and this is more towards the end of the paper. They say that any molecule containing an amount of internal energy equal to or greater than epsilon star may be called an activated molecule. It may not be in a position to undergo the particular reaction which we have in mind. For this may depend upon the orientation of the several parts of the molecule, upon the location of this energy within the molecule, or upon other factors of a similar nature. In other words, the molecule may not satisfy all the conditions requisite for the reaction in question, but at least it satisfies the energy requirement. And this, it's amazing if you actually look at this, because Lewis is actually already talking about orientational effect of chemical reaction. It's 1925. Way before any experiments could have been done. It is today now that sophisticated molecular beam experiments are actually, bringing out this very deep point of view that Lewis already saw. So that was 1925, right? Well, let's fast forward to nearly 100 years later, right? This is Barry Carpenter, Jeremy Harvey, and Andrew Oribin, 2016. And what is amazing, they say the physical mechanism that lead to this energy flow, IVR, in an isolated molecule are not very different from those that lead to chemical transformation. And so in hindsight, perhaps it was questionable whether one should have assumed that the time required for the former should be very much smaller than for the latter, as a statistical approximation requires. And this is again a very deep statement. In fact, it's really interesting, because I remember I was sitting in Calcutta in the Astor Hotel. By the way, fantastic hotel to be at. I have a notepad where I write my thoughts, and I kept thinking, why do people make this claim that this time scale is faster than the IVR, or IVR time scale is very quick, and so on and so forth. And then I realized they are tied together. You can't disentangle these two things. That is the reaction event and the energy flow event. And it was quite a relief to see somebody like Barry Carpenter write the same thing just a few months later. But what is interesting is, though, that doesn't look like there has been any progress from when Smith made this statement. Lewis and Smith made the statement in 1925, and what Carpenter, Harvey, or Ewing are saying in 2016. What is even more interesting, okay, so that's a century worth of work that I'm paraphrasing in just two quotations. A theorist of repute, like Eric Heller, saying this, right? What's Eric Heller saying? He says, over the years, we have found that a useful definition of IVR is whatever experimentalists do not understand or cannot assign, leading to decay, fractionation of spectra, etc. Thus, when certain spectral features are explained theoretically in terms specific mode-to-mode coupling, occurring resonantly and in an orderly way, this is not considered to be IVR, much to the consternation of the theorist. But experimentalists have good reason for this, right? And that's a really interesting statement to make, okay? In a way, I mean, Rick Heller is taking a broad swipe at experimentalists, but I think the way I see it is Rick Heller is really expressing the frustration that theoreticians and I think chemists in general have had with this phenomenon. Okay, but he does end by saying that experimentalists have good reason for this, okay?
So Srihari, can I just, so these are very nice papers and statements you have picked up. Thank you for doing this for many students here, as well as for me. Sure. So don't you think that this is in part because we spectroscopists have a very poor resolution, experimental resolution of states in general. So when we typically of course, with the molecular beam experiment, it's really resolved. You can distinguish rotational states, you can distinguish vibrational states, but once you are looking at all of them simultaneously together in a condensed phase,
right,
the resolution of it is a problem to assign. So IVR and other kinds of very interesting mode-to-mode coupling information are all bunched in together. Don't you think that could be?
Yeah, partly. But in defense of experimentalists, I mean, this paper, this statement by Heller was made in 1999. At this point, in the frequency domain, people are already doing eigenstate resolvement, particularly Kevin Lehman.
Absolutely. Absolutely.
So they had some beautiful, eigenstate results with a very high resolution spectra of very interesting molecules. Right. And I'll sort of, hint at some of them as I go along. So it's not entirely, reasonable that Eric Heller says this, but I think that he made a different consideration. And the point was that when you look at such high resolution, the issue was you had the information, but the question is how do you process that?
Absolutely.
Yes, but I think at the frequency domain, definitely they had fairly high resolution results. Yeah, but what I wanted to sort of catch with this, just sort of this very one slide really, is that it's been a century. And then you have this sort of varied statements in some sense. So it sort of already gives you a hint that this is really a sort of a very interesting problem. Okay. So let's bring up something else which came up very recently, because it's going to be the centerpiece of most of my talk. This is Mark Buchanan in Nature Physics. He gives this little small themes or thesis, and the title is Going into Resonance. Now, he says one of the more surprising things in science is how obvious certain principles can seem once understood, where they were anything but obvious before. This history of resonance is another good example. The idea is obvious now to any engineering undergraduate, but it challenged the best minds in science for over 3 centuries. Now, this is going to sort of capture most of the things that I'm going to say. Particularly, the resonance is going to play, in chemistry, what we call as anharmonic resonances. And you'll see that that is actually at the absolute center for the phenomena that I'm going to discuss. But the thing that I'm not happy with Mark Buchanan's statement is this point that he says that this idea is obvious now to any engineering undergraduate. Now, I mean, I don't want to put down engineering undergraduates, but he should have said any undergraduate, right? I mean, that's sort of, I think he's really pulling a fast one on science undergraduates, isn't it? I mean, so anyway, so I hope he corrects that at some point. But the other point is, he says that the gradual acceptance of resonance as a mechanical phenomenon only took place as a result of dramatic failures in bridges and machines. Okay, so yeah, I mean, that's a very dramatic statement to make. As we will see, resonance is actually responsible also for dramatic breaking of molecules and so on and so forth. But that's a very, very narrow way of looking at resonances. Hopefully, what I'll be able to show you at some point in time is that actually, if you have lots of resonances, they can actually also stabilize your system, okay, instead of destabilizing it. Now, that sounds counterintuitive, but it actually isn't. I mean, that is what is wonderful about resonances. And it certainly happens in molecules. Okay. So let me get to the what, why, and how of IVR. So what is IVR? Don't worry, I just use, I mean, it says IVR, the fantastic phenomenon. I mean, I wrote it in French because I always I'm learning French, and I always thought that things sound so amazing when you write it in French, isn't it? So, so IVR, the fantastic phenomenon. So I've shown you, I mean, methanol as a system here, and there's a reason for showing that. And the idea is that, okay, let's imagine that we actually put some energy down into the OH stretch that might flow to the CH, for example, or it might go over to COH bend, or it might go somewhere else. And the question is, what actually happens, right? So varying amount, but precise kind of excitations of this OH stretch. Well, it turns out that this experiment was actually done already by Tom Wiese and co-workers. And let me show you this very interesting picture that they already have. So what this is showing is the spectra that they recorded for putting 3 quanta of excitation into the OH stretch, 4 quanta, 5, 6, 7, 8, and so on and so forth. Okay. Now, what one takes away from this is that if you look at the general shapes of the lines and the width, the broadness or the sharpness, what you first see is that it's actually non-monotonic. So in other words, if you put more and more excitation into the OH stretch, it's not that as you put more and more excitation, basically, a lot more energy is going to basically flow, and there's a lot more, activity in terms of sloshing of energy. It's actually quite interesting because for example, if you put 5 quanta, it's actually quite see sharp lines, but not only that, as is sort of shown here, you can actually see multiple time scales that involve different modes. For example, you will see about a 100 femtosecond time scale that is associated with this particular energy gap or splitting, about a 10 picosecond and also a 1 picosecond time scale. And what they do in this wonderful paper, in fact, I wrote a series of papers, they explain exactly what these time scales represent. Sorry.
I request all of you to please mute yourselves.
Please
That
mute.
would help.
Yep. So,
Srihari, can I ask a question?
yeah, please go ahead.
So, is this a dispersed fluorescence at the excitations indicated here at nu 0?
Yeah, I think this combination of dispersed fluorescence, and they also do this so LIF, and I think it's an IR initial IR excitation followed by yes, the spectrum I think is dispersed fluorescence. Yes.
Looks like it's a dispersed fluorescence. And interesting part is that if you go on increasing the quanta in the OH,
right,
the character of the dispersed fluorescence, which is an indicator of the IVR or lack of it, is changing.
Yes.
And what is surprising is that 5 nu 1 is giving you very sharp lines.
Exactly.
Okay.
Yeah. In fact, the pi nu 1 already. So what happens is that so what they did was a detailed analysis, and they actually said that these different time scales correspond to this OH stretch energy now going to very specific modes dominantly of this methanol. And what is of course interesting is that lower energy you see broadness, right? And if you go to like the 6 quantum excitation, you don't see the splitting anymore. It's kind of a shoulder, but nothing much. You see the shoulder in the 7. Right?
Can I just interrupt you, Srihari? I'm sorry, could you explain the experiment slightly and give a little bit of the physical picture of what you are doing when you're doing the experiment? Because this is slightly confusing. The stacked spectra are there, I understand, but just for the clarity for everyone. Yeah.
So what basically their purpose, so again, so I'm not an sort of expert experimentalist here, right? So the idea here is that what they do is they actually use a combination of techniques to basically access the overtones. So what they do is they pump in the OH stretching, which is the one that has the oscillator strength. But as students know, you cannot just excite 8 quanta directly. So you have to use methods. So what they actually do is a combination of an infrared. So there's what is called an IR labs, right? And then they pump in 3 quanta, 4 quanta, 5 quanta, 6 quanta, 7 like that into the OH stretch. And what they then do is actually observe, the sort of the spectrum. So this is actually a frequency domain spectrum. It's not a time domain spectrum, right? It's a frequency domain spectrum. And what they observe from the spectrum is, so broadly speaking, what they expect is, as Sanjay was pointing out, that if you see sort of very sharp features, what that basically means is that there is not much of an energy flow, or it's a restricted energy flow. Whereas if you see very broad, like you see for the 8 quanta in the topmost part, that basically means that there is, pretty large amount of energy flow that's going sort of over several modes of this methanol molecule. Okay, that's sort of the basic thing. But again, if you want to know precisely how they do this experiment, I mean, this is the reference, and this is where I think one can find the message that
the only thing I wanted to know was this is detected in the emission, the fluorescence coming down. So you are pumping with an IR and you're looking at an emission afterwards.
So so there is an LIF, so there is an LIF component as well. So they actually ionize then detect the patterns. Yes.
Just one more little clarification, Srihari. So they have transformed this peak widths to get this time widths, temporal widths.
Yes.
Okay.
Exactly.
Okay.
So basically, So
if I can, Srihari, add just one comment about experiments, because this was done by fluorescence.
Yeah.
But if we can do an absorption spectra, you would see the same spectrum.
Yeah. So
basically,
Correct.
Go on.
So basically, the idea to think is that if you could sort of coherently excite this entire band, right here, Okay, and then the point is that you would create a non-stationary state now, right? That would represent sort of the OH stretch with 5 quanta of excitation. And in a time domain, what you would see is precisely these time scales of this energy flowing away from this. That's what it is.
Yes. Perfect.
So the key point, I mean, again, so the point that I put up here wasn't really to sort of discuss this experiment in great detail, but the reason I wanted to show you this was to emphasize that in an isolated molecule, which is not particularly simple, methanol is not a particularly simple molecule. I mean, it has this methyl, and the methyl has torsion, so there are lots of complicated things, but it is an isolated single molecule, gas phase. What you see already is there is multiple time scales for energy flow. It's hierarchical, seemingly. So in other words, it doesn't sort of, it flows in some particular way. Seemingly, there are dominant pathways. And third, it's not monotonic. So it is not that if you put, more and more energy, simply you get more and more IBR or more and more energy flow. So this is not it. There are some, when you even put more energy, somehow it shuts off or it sort of, freezes up. So this is sort of characteristic of IBR. So these multiple time scales, this hierarchy of flow, this non-monotonicity, right? So it very strongly depends upon how much energy into which mode, okay, and what sort of excitation was. So, in some sense, that's sort of troubling, right? Because as a theoretician or a chemist in general, I mean, you want to have some universalities, right? I mean, you want to be able to make statements that, oh, look, okay, if you do this, then you're going to always see this, or you'll always see this sort of a sharp line or a broad line. But that's not the case. And this is something that has dogged the history of IBR, ever since people started making these beautiful.
Harry,
yeah.
I have a question. See, I don't understand when you are at 6 nu 1.
Yeah.
Okay, there is no energy flow into different modes because I just see a single peak.
Yeah, so there is, but it is actually a very long time scale actually. But it goes to some because there is a width to it, right? So it's not a very. I mean, it's the single peak. So basically, let me explain this again. So the idea is that each peak here, the way you should think is that there is energy flow and that time scale. So there is beating. So in the 5 nu 1, for example, when you see this 100 frames per second, that basically is saying that this is coming because the OH energy actually goes into the CH symmetric stretch mode, for example. Okay, so that's where it comes from. But in the 6 nu 1 case, there is energy flow, but it's on a much longer time scale, much longer time scale. Okay, and it doesn't. You cannot obviously identify. I mean, they have identified in that paper what might be potentially causing that broadening in 6 nu 1.
Srihari, if I can, just one more question. Sorry to stop your flow.
Sure.
But at 16,000 wave numbers or 26,000 wave numbers,
right,
the density of states would be so high.
Enormous.
I'm wondering how they were selectively exciting the 5th quanta, 4th quanta, 6th quanta of OH.
Right.
This is really interesting as to how they did that experiment, because I would imagine the density of states at this energy would be huge. I mean, so thousands of states within a wave number, right? So yeah. Okay, go ahead.
Srihari, if I may just add one clarification for Ramses's question.
Yeah.
The fact that these are experimental spectra, these are observed.
Yeah.
So the 6 nu 1 being a sharp peak, though with a small width, implies to me that there are states in which this doesn't couple as much compared to 8 nu 1 or even 4 nu 1.
Correct. Yes.
And there may be symmetry could be a reason. The density of state is not going to be less at 6 nu 1 compared to 4 nu 1.
No, it's not.
So symmetry may really be a reason that they don't couple and the energy doesn't flow to all the states at 6 nu 1.
Indeed. So all of you are right. All of you experimentalists are way better at understanding this. Yeah, I mean, unfortunately, this. Okay, but in fact, you're correct. So there are symmetry aspects here, and as Sanjay said, the density of state is absolutely mind-boggling here because there are torsional modes here, very low frequency modes sitting here. So at 20, 30, 25,000 wave numbers, you have bucket loads of states over there. What the point though is that a straightforward density of states count would say that as you go from this energy corresponding to 3 nu 1 all the way up to 8 nu 1, your density of states should be going up exponentially, right? So which means there are more and more states that are being provided almost to the limit that you have almost a bath, if you want, for this OH energy to sort of hook up to. But This is the beauty of this particular experiment, which I think is particularly nice experiment, because what they showed was that the total density of states actually is not a factor at all. And if you think about it for a second, it does, if you step back for a second, it does make sense, because this total density of states has been nailed into our brain for different reasons, actually. The point of the matter still is it's methanol. It's a molecule. It has locality. There, you have OH, right? We say there is a methyl rotor, right? The point is that the coupling structure is very hierarchical. It's local. The total density of states might be huge, but the fact of the matter is that it's still a structured molecule, not a soup of a bunch of carbon and oxygen hydrogen atoms. This is really why the local density of states is the most important factor, not the total density of states. In fact, this is one of the big points that these people made already, 15, 20 years ago, right? This is one of the key points that they wanted to make. Okay. So can I go ahead?
Actually, sorry, before you change this, I can ask a very quick question. I guess it relates to the previous concepts, but I guess the vibrational wave packets and the corresponding frequencies that are observed here, how do we know that they're, I guess we do not know that they're arising from a given electronic state within that density of states. That they might be arising from, different electronic states.
Very good question. Yeah, no, in fact, they were pretty, so they had characterized it, they made sure this is the ground electronic state, is where they're operating.
Okay, sure,
Yeah.
Vivek, if I can just comment on this. This is a molecule with no double bonds or anything, just all single bonds. So any excited state would be either dissociative or would be very high lying Rydberg states. So in this wave number region, there won't be any electronically excited states.
Sure. So sorry, I'm not familiar with these molecules.
Yeah.
Okay.
No,
okay.
They're definitely in ground electronic states. Yeah. So this is the okay. So let me go to the next slide to show you another example. And this one actually is an example that, Bob Field at MIT has devoted almost his entire life to. This is acetylene. And in acetylene, what happens, again, you can do this very, very, in fact, there is tremendous data, high resolution data, the spectrum of acetylene. And what you see again is that when you actually pump these high vibrational levels of acetylene, particularly, for example, the bending region of acetylene, you see again time scales that range from a few picoseconds to 100 femtoseconds to tens of picoseconds. And the question is, okay, so what happens? So the reason I put up this video is because this is a courtesy of Mike Kelvin thing. It's a very beautiful rendition of what actually happens when you pump. So imagine you have acetylene molecule, and you're going to put a lot of energy into the bending mode. So you have the cis bending mode and the trans bending mode. Okay, so at low energy, it would be exactly what you expect. That's your, that's the normal mode, that's the cis and trans bending mode. So you have the trans bending mode here and the cis bending mode here. Okay. Now the question is, well, naively, suppose you put a lot of energy, you start putting enormous amount of quanta. In fact, they actually put about 20 or 22 quanta or more into this bending mode. Again, there are techniques to do this, right? Very sophisticated technique, and this is something that people in Bob Field's group have perfected actually over the decades. And in fact, they take it almost to the edge of when acetylene is going to isomerize into vinylidene. Okay, so this is right at that edge actually. Okay. Now, what actually happens amazing midway through this is that you would think if you put a lot of energy, so for example, a cis bending mode would just sort of vibrate more and more and more and go much faster and faster and faster and faster and faster. But interestingly, that's not what happens. So it does that for a while, and later the modes actually totally metamorphosize, they change. So as you get closer to the vinylidene isomerization barrier, you get this very interesting local, what is called local bender mode, where one hydrogen is nearly stationary. The other hydrogen is doing this large amplitude swinging sort of, bending motion about the carbon-carbon axis. And then you have this other one, which is really fascinating. It reminds people who have studied basic spectroscopy of what is called vibrational angular momentum. And this is actually counter-rotatory mode. So the two hydrogens are going in opposite direction. Okay, right? Completely unrelated modes. So you can't. So these two modes and these two modes are completely different. In fact, there's a whole bunch of other things that happen here. And then this dance of acetylene is amazing. It's amazing. It happens Now, if you imagine when acetylene has to go over to vinylidene, what should happen? One of the hydrogen has to go over, right, to give you the vinylidene radical. And if you think about it, the left-hand side top, that motion, now if you take it all the way through, if it swings all the way through, this would be vinylidene. In fact, this is the mode that eventually sort of maps onto the reaction coordinate, not this trans and cis low printing mode. So the lesson here already, there were knows, in fact, experimental perturbations on the acetylene spectra due to these new sorts of motions are already known now. So people understand that. And what is interesting is that this sort of gives you a very important message that at low energy, whatever you think about the motion of these novel modes, this collective motion of atoms in a molecule, when the molecule is ready to react, it's getting energized, these modes can change, and they will change dramatically. Right? Incidentally, this happens in many molecules. Actually. And I'll give you one very specific example later on. So again, this is another beautiful example where theory and experiments have really come together to understand some of the most complicated features that is happening dynamically in the system.
Srihari, this experiment was done in gas phase.
This is gas phase. This is stimulated emission pump, combination of dispersed fluorescence, stimulated emission pumping, and now they're also doing stark level spectroscopy to even find.
Okay. Thank you.
Okay. So again, if you want to know sort of a more recent sort of if you want history, a summary of what are all the wonderful things that has happened in this particular molecule over the last 2 decades, this is a very nice perspective to look at by Michel Hammond and David Perry. Okay. Here's another puzzle that I love. This is due to Brooks Spade. And Brooks Spade, being such a connoisseur of IVR, and he is probably, spectroscopist supreme, right? He did an experiment with the students in, 20 years ago now. And what was interesting was that he took a bunch of molecules, okay? And these molecules were sort of large molecules. Let's not worry about exactly what they were. But these molecules came in 3 classes, if you want. One which had planar conformers, one which had non-planar conformers, and one which had methyl rotors. So one set which had methyl rotors. And they actually did high-resolution spectroscopy. They actually determined the IVR lifetimes of the acetylenic CH stretch. So all of them had acetylenic CH stretch. So they actually accessed the acetylenic CH stretch, I believe, the fundamental, in fact. I mean, maybe or the second, first overtone or something like that. Not very high, but these molecules are huge. So the density of states are enormous. Okay. And in fact, you can see on this axis, on the x-axis, the state density is going up to something like 500 states per wave number. Okay. Now, when they excite this acetylenic CH stretch, they ask for the lifetime of this energy, right? How long does it stay there? And what they found was, curiously, it divides up into sort of 3 groups. The molecules which have planar conformation seem to have lifetimes close to a nanosecond. For a nanosecond is, given these density of states, this is kind of living forever. Okay? The ones that are non-planar sort of, lower lifetime. And then the ones that had methyl rotor were actually more like 100 picoseconds or less. And the interesting question that, in fact, this was the data, they presented it, there was a beautiful set of experiments. And what they say at the end of the paper is that as a whole, this data set will provide a challenging benchmark for theoretical methods of calculating IVR rates because of the large range of timescales observed for structurally similar molecules. Alternatively, this series might be useful for testing new ideas for explaining IVR rates. This, incidentally, is one of the least cited papers of Brooks Spade. And there's a reason for that. I don't think too many people have actually come to grips with this data yet, theoretically or experimentally. Why is it that just because it has planar conformation, or one might argue for symmetry and so, as everyone pointed out, some symmetry couplings, but 1 order of magnitude longer lifetime, 2 orders of magnitude longer lifetime? This is not an easy data to understand. And incidentally, this is still a puzzle. I mean, at least for me, and I'm sure for many of you, if you read this paper, you'll see that this is still not a resolved issue. So again, fascinating thing. The molecules show such rich behavior when it comes to energy flow. Here's from the same paper, in fact, but there is a very famous model for IVR. I'll come back to this again later. Don't worry about it. Idea is that you actually access a state which is called as a bright state spectroscopically. For example, this would be the OH stretch that we saw in methanol, or the acetylenic CH stretch in the previous example. Okay, and when you populate the state, you excite this. The idea that people have is called a tier model. So what they say is that you have this bright state and you have a whole bunch of other states that are providing densities. Now, all the densities, remember I said the global density of states doesn't come into picture immediately. It's a local density. Local density. Yeah.
Sorry, I don't understand. What is ZOBS?
It's a shorthand for zeroth order bright state.
Oh, okay.
Yeah. So basically,
and how do you call this thing? I mean,
sorry.
Does a molecule have a single zeroth order bright state, or does it have many?
So it can have more than one, but not a whole bunch of them. So usually there will be only a few that will have the enough what do you call oscillator strength to take on. So for example, in methanol, the OH stretch, the third, 4, 5 excitation, right? 5 new one. This would be the zeroth order bright states that you would access. So they're called high overtone states, for example. So typically they are high overtone states. It's much more complicated to sort of manufacture combination states. But people have done that. The idea is that this is the state which carries pretty much all of the activity, that the light will couple into it. And so you will basically excite this. This is sort of the most natural thing to couple into. So I don't know if chromophore is a wrong term to use, but perhaps you can say this is the chromophore if you want.
Srihari,
okay.
It's like chromophore, and if you do like a harmonic approximation, this would be the only state that would be observed.
That we observe, exactly. Yes. Right.
But there are many other states in the neighborhood.
So the idea is that this is carrying all the oscillator strength, right? So you first populate this. It's called a bright state because this is the one that lights up when you actually shine light on it. This is the one that's going to catch it. Now the rest of them are sort of they're called dark states because these are not the one that are going to get accessible first. But the idea is that because there are these states and there is this local density and there is some way to sort of separate them into different stacks, which I call them tier 1, tier 2, and so on and so forth, right? Then these states are going to couple to this bright state and start sharing this intensity, the bright state intensity. And so the idea is that this is the way the energy essentially sort of flows through hierarchically through these tiers. So this is a model that's been around for a very, very long time. But the reason I wanted to sort of, I'll come back to this again. So, but the more interesting thing here is to look at the right-hand side. This is again Brooks-Pate's result. There are 2 molecules there, and you're looking at the spectra. One is 4-fluorobutadiene. The down below is a 3-fluorobutadiene. Basically, the difference between the 2 is that where you place the fluorine atom. Okay, and the fluorine atom is over here. You're going to place the fluorine atom over here. That's it. Okay. What is amazing is that just that small change, nothing else has changed. So basically, the density of states is going to be similar, right? I mean, it's not going to change so much between these 2 molecules. But look at this. 4-fluorobutadiene lives almost an order of magnitude longer than the 3-fluorobutadiene. It's just that the energy flow is so much more active in the 3 position than in the 4 position. Now, this sensitivity is what makes, so you can say maybe it's an electronic effect, okay, but it's certainly not a density of states argument. Okay. But what is interesting is that this is again a puzzle, which as far as I know, I haven't seen a resolution of this. Okay, so in other words, a theoretical resolution. Exactly why? What is it that the pathway, what is it about 3-fluorobutadiene that opens up so much more pathways for the energy to flow, which is not there for the 4-butadiene? This is still, as I said, they are sort of interesting observations. Okay.
Hi, Srihari?
Yeah.
Can you just go back? So in this slide, how do you distinguish in a molecule the 0-order bright states with the tier 1 or the tier 2 states? And how do I, if I see a molecule, how do I know which is tier 1 states or 0-order bright states?
Yeah. Okay. So what happens is, okay. So I'll give you a very short, maybe even a cryptic answer, but later on, and perhaps not today, but tomorrow I'll get to this precisely. So there is a way to essentially, if you want, prioritize the states based on a perturbative coupling estimate. Okay, so the tier 1 state would be the ones that would be the most strongly coupled to the bright state. The tier 2 would fall into sort of the next class. So it'll be weaker coupling directly, but they will be coupled to the tier 1 states, right? So you have some sort of a pruning, if you want, of the set of states, and you prune them and then separate them into these ladders. Okay, these sort of stacks. So the criteria is based on sort of, if you want, it is actually a perturbative criteria, and people have come up with different sorts of criteria, but they're all some sort of perturbative criteria in one way or the other.
So I just want to ask, so is it some kind of anharmonic coupling between these states, or am I wrong about that?
Yes, yes, sir, it is. Of course it is. It is the anharmonic coupling, but what you do is basically you estimate the coupling relative to the, like you do in second order perturbation theory. This is basically the magnitude of the coupling, anharmonic coupling, compared to the energy width, right? Energy spacing.
Okay.
Zero energy spacing. And basically based on that, you sort of, say that these are the first tier and then the second tier and third tier. And so on.
Okay, thanks.
Just to, I guess, add a question. So this looks very similar to very recent like effective mode approaches from Burghardt and Cederbaum and so on. So my question is, so at least I'm like more familiar with their formalism. So in their formalism, it's about electronic degrees of freedom talking to certain vibrational modes. So then they have tier 1 modes which directly talk to electronic degrees of freedom. But then they have these tier 2 modes which are coupled to tier 1, but they are also mutually bilinearly coupled. So is it similar here as well? Or?
Right. I think the thinking is similar, right?
Okay.
Basically, because you want to come out with a hierarchical scheme for the coupling, not like everything coupling at the same time, I believe.
Yeah. Okay. So here also like tier 2, for example, would be all mutually bilinearly coupled set of modes.
Yes, they can be. They can be. I mean, but the more important point is that this separation between tier 1 and tier 2.
Sure. All right. Thanks.
Yeah.
Just a quick question. Like, if I just correlate it with coupled springs, something like that, and think in terms of FPU problem,
right?
It should not be just unidirectional. Like there should be recurrences, at least locally.
Yes, that's a good point. But the point is that this is sort of a very old model, right? And in fact, the expression that I've written here is the golden rule rate for basically golden rule estimate. Okay.
So that's already statistical.
So basically, the idea that people thought was that essentially IVR is fast. Okay, once it goes out, it's essentially irreversible. So it's not really going to come back, right? So the picture is therefore sort of there is this unidirectional flow. But you're right. I mean, this is not entirely true. So there are subtle correlations. These are indicated by, for example, the orange dash arrows. Okay, and this is actually coming out of more recent research. So this is added on. But the old model was essentially you have this huge path of states to couple to, and once you flow out into them, there is very little chance it is going to come back, back to the right state.
Okay.
Yeah. Okay.
You certainly know it better than anybody else. Fermi Pasta Ulam told even those days that it can come back, isn't it?
Yes.
Yeah.
And the interesting thing is that when Fermi Pasta Ulam was saying that, it's exactly when Rudy Marcus was telling us that RRK
that's all
same time.
It does come back.
Yeah. Well, two completely different directions.
Surely, Professor Sebastian wants to say something. Professor Sebastian?
Yes, actually, I mean, when you look at the tires, it must be true that the coupling matrix elements decrease.
Yes. So there is a particular scaling one can actually sort of work out at scaling roughly, right? So, but it's so there are factors here. Yes, indeed. So it depends upon what kind of anharmonic couplings are there. So what order, for example, are they cubic?
No, but no, I mean, at a very simple level, can one construct a simple analytical model? I mean, of course, I know the couplings have to be artificial. Has anybody done that?
Yeah. Oh, absolutely. So Martin Grubler at Urbana-Champaign actually has already come up with a scaling model, right? So where you can actually put down a scaling relationship between the couplings that should sort of take you from sort of one tier to another tier to another, right? So there is actually a specific scaling of these things, and it's already there, and there are many others. So including, I'm not sort of saying that here, but for example, the original Bixen-Jortner model that was there many years ago, they were already sort of imagining that you have these tires in some, you can construct these tires in some sort of stacks of states with some room, for example. Yes.
And how old is this? I mean, Grubel's paper.
Grubel's paper is late 90s, I believe, to mid 90s.
Okay, fine. Thank you.
Yeah. But again, even in the Bixen-Jortner model, you will see that even Rick Heller, when he was working on this thing, you would see that there are models that people are putting to sort of construct these tiles, right? So you can do that. Okay. Now, why is this? So this is sort of giving you a hint about these things, but clearly one of the reasons that IVR is so important, and I'll sort of paraphrase this very quickly, is that, for example, in reactions, okay? So when you think about, for example, Uni Molecular Dissociation, suppose it's a very simple molecule, it's a triatomic molecule that's going to fall apart, right? So one of the bonds is going to break. And the question of interest is what is the rate constant? In this case, you could ask, well, it's either the thermal rate constant or the microcanonical, it doesn't matter, connected. So let's say it's the microcanonical rate constant. And this is the famous Lindemann-Hinchelwood scheme that everybody knows, just sort of with a modern rendition, if you want. And the idea is that you have the molecule, it gets activated, it becomes an active molecule, which means it has enough energy really in it. And if this energy gets into the reaction coordinate, then that bond will break, like it's shown here. But the important point that really was emphasized by Marcus, and this was the essence, if you want, heart of RRKM theory, was that this molecule, which has now this lot of energy now, a sufficient amount of energy, this has to somehow find its way, channel into this bond that's going to break, okay? And this process is the intramolecular vibration energy flow, and it has to happen. If it doesn't happen efficiently, this rate is not going to be, so good. So the whole idea is this, and Marcus, of course, realized the complexity, dynamical complexity of this problem, and so he made what is now a very famous approximation, where he said that the time scale when you cross the transition state, which is the reaction time scale, if you want, this is the time scale for crossing the activated state or the transition state, this is much, much slower, larger compared to the time scale over which the energy redistributes to bring it down into this bond. Okay, so that's sort of the key assumption. And it turns out, of course, then you get this very famous expression of Marcus. This is the so-called RRKM rate. But notice is something very interesting. This innocuous little assumption that Marcus, of course, very cleverly made, okay, that actually results in dynamics disappearing. Dynamics literally disappears in that one approximation. Okay, and so we will come back later to this, but this just to show that both IVR plays a very, very important role in this. And of course, experiments are beginning to question whether this assumption is true. How true is it, or how much, if it's not, how much is violated by it, and so on and so forth. And there's an enormous amount. Let me sort of skip this for the moment. It's just sort of giving more of this. We'll come back to this later. Okay, I just want to present something which is different from CAS phase. So this is solution phase. Okay, this is actually an experiment that was done by Dan Singleton and a student a few years ago, and this is actually a condensed phase reaction, not a CAS phase reaction. So what they did was, so they actually create this what is called as a primary ozonoid, and this primary ozonoid actually is an intermediate. Okay, and now this particular molecule, okay, this can actually cleave in different ways. If it cleaves in part, this OO bond is broken, right? You would get these products. That is, say, product A. And if you break this bond, you get actually this product. It's a different set of products entirely. Now, what is clever about this experiment was that they actually attached a R group over here, okay? And they varied this R group from sort of a methyl all the way to a really bulky group. And what they wanted to know was, well, what is actually the branching ratio, that is, between this product and that product. It turns out they don't have the same barrier height. So if you look at the barrier height, they differ by about 6 kcal per mole. Okay. Now, what people typically assume is that this, look at this one, this is 57 kcal per mole. This is pretty high. Okay. So the ozonoid is going to come in hot. And the idea was, people say, well, this is first going to cool down. Now, the idea is that if it comes to this sort of fairly deep well, and if it cools off, thermalizes, that's the fancy word for it, thermalizes, then essentially, the barrier heights are going to determine the branching ratio, and that's that. So in fact, what you would expect is that the A has a smaller barrier than B, and therefore A to B ratio should be larger than 1. And that's okay, so that's fine. Now, what is interesting about this is that when they varied this R group and they looked at, so here's the column which shows the experimental branching ratio. And you see it's, 26 as expected, right? And so on and so forth. Now, what is interesting is that if you do naive transition state theory, now I will not get into exactly how this calculation is done, they give a lot of detail, but if you just do naive transition state theory, you're way off the charts. You're 5 orders of magnitude off the charts, okay? This is not going to get it. So they said, okay, no, we have to do the transition state theory as Marcus would do, which is to basically, since we have to worry about whether this actually thermalizes or whether the energy sort of flow happens sufficiently rapidly that it cools down. So they did an RRKM calculation, and lo and behold, this is wonderful, because what they saw was that, well, this first number is not bad. Second number is also in the ballpark. That's very encouraging. There is an increase. So the numbers don't actually match exactly, but there is an increase, right? Which is in the right direction, okay? And even the 3,7 dimethyl octyl, right? It's fortuitously correct, okay, 61. But the shock was when they went to the bulkiest one. Now, remember, I just said in RRKM, the assumption is that the IVR actually happens and happens literally instantly. So it just cools off very efficiently. If RRKM was correct, then this bulky group should have actually shown something like that, okay? That kind of a branching ratio. In fact, it doesn't. Experimentally, there is hardly a change when you go to bulkier and bulkier groups. In fact, this between 3,7 dimethyl octyl and this one, there is almost no change, if you want.
Srihari,
yeah.
Can I just ask you a question now?
Yeah.
See, when you go from gases to liquids, there are more complications.
Sure.
In terms of friction, and they don't move as freely. So neither TST nor RRKM should work.
Yes,
do they worry about frictions and other
yes.
things here?
Yes. So the RRKM estimate actually takes in several factors into account, which account for the surrounding condensed materials. So this is not a run-of-the-mill RRKM. This is actually RRKM with very carefully, the other effects are taken into account. So the details are there actually in Dan's paper. Okay. So they do actually take into account sort of the time scale associated with this intermolecular couplings that might happen, and they actually did dynamics as well. So it's an experimental work, but they actually did ab initio dynamics as well on this, run some trajectories to get some dynamical data and so on and so forth. So it's a more carefully done RRKM and not completely ignoring the condensed space. That's
viscosity, for example.
Yeah. Sorry.
Viscosity.
Yes.
Flow, everything it's included.
So they have taken the surrounding solvent effect into account for sure. Yes. Yeah. I mean, I would say this is taken on sort of at a level which is sort of microscopic, in terms of actual solid molecules, but it is taken into account so that it is not completely ignored either. Yeah. So it's there. Now the conclusion.
There is a question from Jaybir. Jaybir, you are unmuted. Jaybir.
No, sorry, it was my mistake.
Okay. No, I just wanted to make a comment here, Srihari. I see all the faculty members are getting tremendously involved, but I also want the students to ask questions, because that would be the real purpose, that let us not get lost in. So I appeal to all the students, ask your questions, and of course Srihari is proceeding with the talk. You can do it afterwards as well, but you can also interrupt in middle.
Yeah, I'll be happy to. Yes. Yeah, thank you. Yeah, so the point that I'm trying to make here is this, that what they basically concluded was that as you make this side chain here, this bulkier and bulkier, actually the energy that you put into this ring mode, that this is the most energy that comes with this particular intermediate, right, this ozonide, it actually doesn't flow down the alkyl chain at all, actually. So basically the one basic assumption of RRKM that all these modes are going to get this energy pretty fast, in a fast enough time scale, this is not true, even in solutions. Okay. So, I mean, 50, 20 years ago, people are saying energy flow, you're studying isolated gas molecules, therefore you expect deviations and all. But this is in solution. By the way, this is not a one-off either. There is now dozens of experiments which are now showing that the assumption that radicals which are formed in condensed media in organic reactions, which people always thought that they will thermalize or cool, this is not true. This is not true at all. Okay, and there is experimental proof, not theoretically. So again, energy localized on the ring modes, it does flow for a couple of carbon atoms down this R chain, but really not any further. So again, even in reactions in solution, this energy flow problem is not an obvious thing, and one cannot make assumptions, depending upon the global density of states or size of the molecule. Okay. Again, this also goes against sort of what is people always thought, that if you make the molecule bigger and bigger, I mean, this is a big enough molecule, right? Bigger and bigger and bigger, and you put it into solution, I mean, of course, everything should sort of fall into place. So all the assumptions that one makes, incidentally. Okay, but this is not really true.
So just a quick question. So it doesn't flow means it gets trapped momentarily at least?
Well, it actually doesn't proceed to, for example, beyond the second or third carbon atom, right? So they suspect that, putting a long alkyl chain there, I mean, it's there just for decoration purpose only. I mean, and as far as the energy is concerned, it's not shared. It's not shared between those.
Srihari, could I?
Yeah.
I mean, what is a solvent? I mean, is it a monatomic liquid or what kind of solvent?
Oh, good question. I don't actually remember this. Yeah, I don't remember this.
Because I mean, if I had vibrational degrees of freedom, then in principle, the energy can be transferred there.
Oh, yeah. So it is. I don't think it's a monoatomic fluid. No, it's not. It's a honest to goodness solvents that organic chemists use. So this is, I mean, Dan Singleton's a serious organic chemist. So yeah, this reaction is spread out.
Srihari, even with
monatomic solvents.
Srihari, even with monatomic solvents, you will still have acoustic kind of modes which can actually take away the energy.
Yes, they can. So this is surprising. But I mean, of course, the question is that what frequencies they come at and what frequencies. I mean, you have to have that. So this is exactly about, for example, the resonance matching that should happen for the lowest frequencies.
The
and
acoustic frequencies will go, probably starting from 0 to some small wave numbers.
Very low. They're very low. Yeah. So in order to access them, the real skeletal motions of this large bulky thing has to somehow couple into it. But then the problem is that the initial ring mode energy has to flow to them, right? For them to then start talking to these low modes of the phonon.
Yeah.
But that's not what's happening, right? Yeah. So they're cold, if you want, in some sense. Is that fine? Okay. Right. Okay. So again, I mean, for those of you who are really interested, I'd recommend reading this paper because, oh, I'm sorry, I apologize. Somehow my reference is incomplete. I'll correct that tomorrow and I'll put it up before the talk. Okay. I apologize for this. Yes, this is a fairly recent paper. But what is interesting is that this is again, a paper that indicates sort of fairly careful methods, careful experimentation, and careful analysis. And there is basically no way out. In other words, you cannot sort of cook up any other argument which will explain why the disagreements is so much. Right. Okay.
Sorry, just a question.
Yes.
So you're saying that it doesn't flow beyond 3 carbon atoms.
Yeah, 2 or 3. Yes.
2 or 3. Then why are the experimentally the values are different, right?
Yeah. But you see, experimentally the values are not all that different, no? I mean, it is not like they're by a factor of 2 different. I mean,
no, there is a trend.
There
is a trend.
Yeah, there is a trend. But I mean, if you look at it, it's 47, 54, right? So if you go from ethyl to butyl, right, there is a jump. And then from butyl, it is slowing down. You can see this, right? It's not really changing. So when you go from octyl to the next big one, I mean, it's a similar change. So it is, so in other words, there is nothing dramatic happening there. So in other words, what the point is, if it had actually flown down, then RRK would have sort of told you that change should have been much more major.
Exactly.
That's not what is happening. Yeah. That's not what is happening. Right. Yeah. Okay. So yeah.
I am Amber here. Just very curious quickly on what are the timescales we are talking of here?
Timescales of
the reaction, like.
Oh, you mean the reaction rate constant?
Yeah.
Oh boy, no, you got me there. I don't remember the number. Sorry.
All right. Yeah, sure.
Yeah. You want to so focus on the branching ratio that you forgot about what a K and KB are. Sorry. Yeah. Okay. I don't remember that. Okay. So, all right. So yeah, I mean, that was sort of the intro. Okay. So, but I'm glad. I mean, this is wonderful. So many questions. I'm very interesting. Okay. So now the question is, okay. So energy flow is there, happens. It's important. It's very interesting. Lots of puzzles. There are things that we don't understand, not just in gas phase, but also in solution phase. Incidentally, this is true also of reactions happening on surfaces. So there are wonderful experiments by Ren and Beck's group, for example, where they show that, in fact, you can have more specific chemistry happening on the surfaces. Okay. In fact, even very recently, in even reactions which sort of I did not know. For example, there are what are called detonation reactions, shockwave reactions, right? In fact, Krupa has published a very nice paper recently where she actually shows that this detonation reaction that happens where the phonon modes actually have to couple in from the solid phonon modes. I mean, this is incomplete. I mean, that takes hundreds of picoseconds. So this is not instantaneous at all, even in a detonation reaction. So there are, huge, hugely, wildly different reactions, conditions where one is now seeing that the energy flow is actually not structureless. It's structured, it's interesting, and then it is begging for explanations, actually. Not easy, but it is definitely out there. Okay, so how does this happen? Why is it happening? Okay, so let me now switch on to my Blackboard mode, right? Trust me, these are not two different talks. These are same talk that I made. I switched to Blackboard mode because this is now where I'm going to explain things on the Blackboard, which is what I would have loved to do personally, right? Much more difficult on e-boards. But anyway, so here's the thing. So this is a beautiful picture which indicates all the complications, if you want, by Friedrich Temps. Here's a ground potential energy surface, potential conical intersection here, lots of things going on, but forget the excited state for the moment. Here's a ground potential energy surface. The way we think about this at the minimum is that you can approximate the potential, this multidimensional potential, by a bunch of uncoupled harmonic oscillators, which we call as normal modes. Incidentally, for students who are thinking, where is the mass, where is the frequency? This is how you write normal modes. This is dimensionless coordinates. Okay, they're all scaled off or scaled away. I'll restore them a little later. So it's uncoupled harmonic oscillators. Now, what happens when you go up in energy is that this uncoupled harmonic oscillator assumption doesn't hold anymore. Okay? What actually happens is you have to take into account the higher order couplings that are actually there in the potential. And they come as cubic terms, quartic terms, and they can keep on going. I mean, this is an entire slew of them. Each one becoming more important as you go up higher and higher in energy. So now what happens? So what are these coefficients? For example, this cubic coefficient is simply this cubic derivative. And these are what people will compute. For example, in quantum chemistry, it's called force fields. Okay. Of course, these are anharmonic force fields, but this is something that people do compute nowadays. So the idea is that this picture that you have uncoupled harmonic oscillators, you cannot hang on to the picture as you go up towards reactions or high energies where things are going to isomerization or bond breaking, because uncoupled harmonic oscillator is simply incapable of breaking. Okay, that's never going to happen. So anharmonicity has to come. Right. Now, there are various ways of looking at this Hamiltonian. So the way I've written, of course, is that now you can write this Hamiltonian itself as, again, these harmonic oscillators plus higher order terms. Now, what is interesting is you can see there are diagonal terms here. So what one typically can imagine is that you can take the diagonal term and shift it over here, right? And create something which is like this, which is sort of equivalent to this, except that the zeroth order Hamiltonian now represents an harmonic. So they're not harmonic because they will have, for example, Q cubed or Q4 to the power of 4 and things like that. So these are anharmonic oscillators now, but they're still uncoupled. That's the important point, but they're anharmonic. And then you have truly these couplings between the different modes. Okay. Now, for sake of simplicity, I'm showing only the vibrational modes. And what is also known in this field of energy flow is that it is really the vibrational modes that participate. Yes.
Sorry. So you are making something like a Hartree-Fock approximation. Mean field approximation for the unharmonicity when you take H0.
It's not quite mean field because so I don't know what you say by mean field at this point, because you're basically taking the diagonal terms and putting into the
but you're not taking like Q squared times Q expectation value like that.
No expectation values. No expectation. No, not expectation values. No, you can take the diagonal term, for example, Q1 cubed, and you're shuttling it to the H0. Yeah.
So, but will that give you this thing, harmonic oscillator solution?
No. So the anharmonic oscillator is no longer a harmonic oscillator. There's no harmonic oscillator solution now.
So no more Hermite polynomials and all that.
No.
Okay.
But this is like a uncoupled anharmonic oscillator.
So you can, for example, you can think of these as coming from imagining the vibrational modes to be.
Yeah. Okay. Diagonal. What you are saying is diagonal anharmonicity.
Correct. Diagonal. Yes. Exactly. So
if I can interrupt one more time, of course, vibrations are important, but you're overselling them, I think, because
I don't.
Brooks-Pate's data, the methyl rotor did show a difference.
Yes.
Even though it was planar.
Yes.
So the angular momentum is a killer. We will get to that later. Anyway.
No. So the rotations are also involved. So particularly when you have methyl rotors, right? And for example, you have what are called the torsional states can mix with the vibrational states and create what are called cryptons. So yes, so they are involved. They do get involved.
Also, when you go beyond the initial conditions, when you go a little higher in energy, it becomes difficult to distinguish between bending and rotation, as is classic case being the was it called a resonance and in CO2 you get that Raman mode.
Yes.
Of course, Arunan's statement is valid that you must keep the angular momentum conserved. I suppose that's one of the important factors that Marcus brought in, bringing the angular momentum in addition to energy.
Yes. So in fact, you can present. So honestly, if I had to start here, I would start with the Wilson-Howard Hamilton. Right? So that's where I would start.
Srihari, since I didn't want to interrupt until now, since I have stepped in, I was curious to know, RRKM would talk about active modes versus the inactive modes, Instead of a 3n-5 or a 3n-6, we will have S active modes to fit the experimental observations.
Yes.
What happened to all this S? Did the S change in all these pictures or?
No, it's buried in this picture. So one of the reasons, so yes, you are right. So you can fit an effective S, right? And this would be less than the usual 3n-5 or 3n-6. But what was begging for explanation is why is the S so low, for instance, right? So in many cases, what happened is that if 3n-5 or 6 could be in dozens, but the effective S would be only 5, for instance.
Yeah.
So the question was, why is it so low? A, and B, the fitting with this effective dimensional, effective number of vibrational mode doesn't tell you about the identity of these modes at all.
Yeah, it's essentially a fudge factor.
It's essentially, exactly, yes. So part of the problem was that you need to know the modes, which modes are coupling, because then that is the most important thing when you want to control the reactivity.
Srihari, just a question.
Yeah.
You mentioned that the energy doesn't flow beyond 3 or 4, maybe 2-3 carbon atoms or 4 maybe. But all this mechanism, in all this what you are saying, how will you, what prevents it from going beyond?
Yeah. So that's a big question. So what is blocking it, right? Clearly the density of states is there. There are states there. Even if you factor in symmetry and so on, so forth, there are states to couple. So question is, what is blocking it? And and that's sort of really the big puzzle. That is what it's not really completely understood yet, right? So that is why these different experiments are giving you different things. If you in the same molecule, for example, if you pluck a different mode, right? It would not respond even beyond 1 carbon atom, for example. It's possible, right? So this is exact. So in other words, people realize that you cannot just brush away the dynamics of energy flow by saying it's fast enough. That's just too coarse and that's just too bland for the kind of experiments that people are doing with the kind of resolution. And that no longer is tenable. Okay. By the way, there are some systems where this is true. And it's again very interesting to know exactly why those systems agree with RRKM so well. I mean, so both ways. See, when Marcus made that assumption, right, he didn't get into the mechanism of energy flow. That what mechanism would ensure that it is fast enough, or what mechanism would ensure that, as Sati was saying, that some modes are essentially inactive or some are adiabatic and so on. So he didn't get into the elaboration on that, because rightfully so in the 1950s, Marcus realized even for somebody like Marcus, that was just too difficult a question to answer. Yeah. So the point is, so again, as I said, so I'm focusing on vibrations here, but this is true that you can actually, in fact, Ned would be the right person to say. So you can start with the Wilson-Howard Watson Hamiltonian, and this is to answer Arunan's query. You can start with that, Arunan, by the way, and then you can actually start sort of building from there and do perturbatively get to effective Hamiltonians like this, which will have the influence of, for example, the rotations and Coriolis and things inside these coefficients now. Okay, so that can be done. And that has been done, by the way. That has been done. Okay, so So the idea is that, okay, so you actually have a Hamiltonian like this, and there are, so lots of issues here. So as Arun pointed out, so one other thing is, why do we use normal mode representation? Could we use a local mode representation? Okay, so again, these are issues that I want to get into right now. They're important, they're interesting issues, but not right now. But it is understood in some sense that neither of these limits, normal or local, is good enough, and the molecule is doing its supreme dance before reacting, incidentally. Both are two extremes that can fail. Second, I will be talking about ground electronic state. You might say, well, what about excited electronic state? Well, true, excited electronic state also, out here has its own topology, shape, and frequencies and couplings. And if your wave packet gets there, or if your system gets there, it's going to experience a different IVR. And that is true. This is going to happen. The key point, though, is that when there is a canonical intersection, then what happens, right? So how do you do this? But it's actually very interesting. So the question, so in fact, people have started to look and analyze, actually, when you have this coupling, how you can understand IVR from sort of both, at least two states and so on and so forth. I won't get into this in this particular talk, but maybe I'll throw in a reference later on, not today, but tomorrow, to indicate this. So there is sort of very interesting ultrafast dynamics that can happen there, but this is sort of, before this ultrafast crossing that can happen through this canonical intersection, you can have very slow IVR happening even in the S1 state, for instance. Okay, and that is going to influence the overall things. Okay. Well, okay, what do we do with this? So let me sort of show you. So this is sort of a general thing. So for students particularly, I wanted to show you exactly what happens. Suppose you take a simple. So let's take harmonic. Start with that. We'll just take two harmonic oscillators, and we'll just take one of these couplings here. So we'll call it the off-diagonal coupling. This is Q1 squared Q2. So, and we'll look at the quantum mechanics of this. Okay. So what does the coupling do? That's the question. Now you notice that if you think about harmonic oscillators, then you have this very nice creation, destruction, or ladder operators for each mode. I call them A1 and A1 dagger, A2 and A2 dagger, right? And what we know from basic quantum mechanics is that the position is essentially proportional to this combination. This is how we express them. So this product is something like this. If you expand it out by remembering that A1 and A1 dagger don't commute, and similarly A2 dagger don't commute, and so on, usual quantum mechanical, what you find is that there are three states, which are three sets of states which are connected. So you have one which actually has this, which is it's shown as a sort of a cartoon. So you have the first oscillator that goes up by 2 quanta, okay, and with that the second oscillator actually loses 1 quanta, or the first oscillator goes down and the second oscillator goes up by 1 quanta. You can have both oscillators getting excited by 2 quanta for first oscillator, 1 quanta for this, or both going down. Or you can have this sort of interesting situation where the first oscillator doesn't change, but the second one sort of goes up and down. Now, what is really interesting is that if you look at this lattice here, so what I'm showing the same thing here, what I've shown here is what you would call as the zeroth order quantum number. So what do I mean zeroth order quantum number? This is the quantum number that is associated, oops, can go back, okay. What is associated with this harmonic oscillator. So you can think of this as the quantum number associated with harmonic oscillator. 1, the vibrational quantum number. This is the vibrational quantum number associated with the harmonic oscillator 2. And it is going to be a lattice, right? Because it's integers. Let's say this is our state. This is our initial state, some N1, N2 that we picked. Now, what is color codes you see here? These are exactly the states that I showed you, okay? So in orange and in yellow and in blue. Now, in fact, if you look at the zeroth order energy, and for the moment, I'm just leaving the 0 point energy away, so don't worry about it. It's just a shift. So let's not worry about it. This is the dependence. And as you can see, this constant zeroth order, so if you say this is some energy that I picked, which corresponds to this N1, N2, this is actually a line in this space, in this lattice. And as all of you know, this is sort of a basic geometry, right? This is a very basic geometry that this particular line will have a slope that is determined by the ratio of omega-1 and omega-2. Now, what is known, this is just simple geometry, that if the ratio is irrational, then you will have this line will never intersect an integer lattice bond. But if the ratio is rational, so for example, here I've set something like this is omega-2 is 2 times omega-1, so the frequency ratio is actually rational, right? Then you can actually show that these two states, which corresponds to this scheme here, these connected states, they are actually degenerate with this state. So what does that mean? So as all of you know, in perturbation theory, if you have degenerate states, right, these are the ones that are going to be the most important ones, whereas these two states are simply going to get pushed away into some small shifts and so on and so forth. Okay. Oops. Okay. So what does this coupling therefore do? This actually coupling leads to energy flow, as you can see, and particularly for this choice. Now, this is very strong mixing, and in particular, there is reason to say that you don't really want to do perturbation theory here at all, and it will become later clear later on. So what happens? N1 loses or gains 2 quanta, and concomitant to that, N2 will actually, either lose or gain or lose 1 quantum. So basically, what has happened is that if you go this way, the second mode gains energy, the first mode loses it. If you go this way, the second mode actually loses energy, the first one gains energy. So what is this condition actually? This condition is nothing but the condition for locking of the frequencies. In this case, it's an harmonic oscillator, okay? But this is the first example of what you call a resonance. This is a resonance between 2 frequencies. Usually when you think of resonance, you say, well, one frequency matches the other. But there's a more general thing. This is called frequency commensurability, frequency locking, where you can have, yes?
Srihari, sorry, could you use a bigger pointer because we could not follow the things on the black background.
Okay.
Maybe your pointer. Can you use the pointer again? Yeah, just or draw. Maybe annotate on it. Can you annotate?
Let's see. Can I annotate? Okay. Maybe I can annotate. Okay. Does this work?
Yes.
Oh, yes.
Yes, we can see it. Yes,
see it?
yes, we can see it. Maybe a color choice would be better, but it's okay. Green we can see. Yeah, the green color.
Should I use like red maybe or white or something?
Yeah, red would be good. Red would be good.
Okay, good. Let's see. Red, and I'll use.
Sorry, I just interrupted.
Yellow. Okay. Yes, yellow would be better.
Yeah. Okay.
Okay. Let's use yellow then. How's this?
Yeah. Perfect.
That's good. Okay. So
perfect. Let's use this for tomorrow also. So just for the sake of.
Okay. Yeah. Perfect. Thank you. I mean, I didn't realize when I switched to black, the blackboard, the pointer.
Yeah. That's okay. That's okay. Okay.
So the idea is that you have this state, right, and this state, and this state. They are now degenerated. They're going to mix very strongly. This is a perturbative thing. So what I was basically saying is that this condition that frequencies are locked here, okay, they are locked means that they are actually locked in resonance. And this is exactly what is going to shuttle energy between these two modes. And this is essentially what this coupling is doing. Now, another way of thinking about it is that from a time-dependent perspective, if I were to prepare this initial state and I were to propagate this, okay, if I were to propagate this, then I would see that that energy will actually populate these other states, okay? And it turns out that you can also ask, well, for this system that I had, simple 2 harmonic oscillators with this coupling, I can determine the eigenstates numerically, for example, by putting down some basis, use the 0th order basis here, which is essentially the occupation number representation, right, N1, N2 basis, right? And then you will get some coefficients, and as is well known, you'll get eigenstates, linear combinations of this. What is interesting is that this particular energy flow that is happening is encoded into these coefficients. And that should not be surprising because, right, so so the eigenstates are essentially, talking about energy eigenstates, so you're in frequency space, and the dual of that is the time, okay? And they're linked by a Fourier transform. So essentially the eigenstates have the infinite time dynamics encoded into that. And that is sort of burnt into these coefficients. And incidentally, this is the sort of high resolution frequency spectrum when people do in scan, they see this intensity, they actually do this eigenstate resolve. This is exactly what they actually determine, the C and alpha. And therefore they can backtrack and find the time dynamics. And this is exactly how the spacings and so on and so forth are showing in the second slide, sort of translates to that. Sorry,
I have a quick question. This is Mangal Sundar.
Yeah.
But you are describing Fermi resonance, essentially. But my worry is when you say that the states are coupled,
right?
It's a polyad of many such, not only N1 plus or minus 2, but it can go further up and further down as well. So why are you localizing this?
Yes, you're absolutely correct. So every state you will see this sort of locking that will happen. In fact, there are many states that you're perfectly correct. But this is just to illustrate that how.
No, I'm just trying to understand. So this is model within the 2-state system. Essentially, you are locking this up to a 2-state system where one of the vibrational angular one of the vibration state is N1 and N2, and the other is N1 plus minus 2 and N2 plus minus 1, because it's, you have Q1 square, isn't it? You had what? You had Q2 square or?
Q1 square, Q1 square.
You had Q1 square, Q2. That's right. Therefore, it's 2 omega 1 is equal to omega 2. That's correct. Yeah, that's fine. Sorry, I had to leave because there is another meeting. I thought this was an important question for me to understand.
No, thank you.
Fantastic talk. I will join you tomorrow. Yeah.
Thanks. Thank you. Thank you.
Srihari, since Sundar has already brought this Fermi resonance in, I was talking about it in CO2. This is applicable only for the low vibrational.
Absolutely, absolutely, yes.
Moment you go up, this gets destroyed.
No, it doesn't. So I'll come to that in a moment, right? So CO2 is very special. In fact, that is the reason it's called Fermi resonance. CO2 is very special because of this fact, and Fermi was the first one to point this out. CO2, it happens that already at the basic fundamental level, the frequency are an almost exact locking.
Yeah.
That's very special. CO2 is very special. Now,
no, I think I will agree with him that it doesn't get destroyed, but in fact, its effects are much more pronounced in the higher energy state, where you have not only regular dynamics, but you will get a fantastic chaotic dynamics if you keep Fermi resonance, because this is the first example where 2 degrees of freedom will actually give rise to nonlinear effects very quickly. Srihari, is that correct?
Yes, absolutely, absolutely. Mangal, you have fast forwarded my talk already. Yeah, so I'll
sorry. I have to leave, so I'm sorry. I have another meeting at 4:30. I mean 6:30. But it was a fantastic talk. I'll join you tomorrow.
Okay, sure. Thank you.
Thank you.
Srihari, if I just can take one more minute.
Although Sundar is leaving or left.
Yeah.
This was I have mentioned this to you. This was part of my PhD thesis problem. Where the bending mode gets strongly coupled with the symmetric stretch mode in CO2. And Sundar already mentioned that this leads to a lot of chaotic dynamics. Of course, I was not allowed to publish this because somebody else was working on it. My supervisor told me, since we knew he was working on it, it is not fair for us to publish. But this was before the days of chaos came in. All I knew was that energy was flowing from symmetric stretch to bending and vice versa, but it wouldn't flow into the asymmetric stretch.
No.
The last sentence I would like to mention is that if the anharmonicity doesn't change much, you can preserve this W omega T2 equal to 2 omega 1. But if the two modes have different anharmonicity, then of course what I said is true.
Yes. So again, Sati, that's very prescient of you. That is going to be my next slide. In fact, molecules, the vibrations are anharmonic for a great reason.
Srihari.
Yeah.
See, what you are actually talking about is quantum resonant tunneling, right?
Yes, Ramsesha, exactly. Yes.
But when it's chaotic, is it still, you don't have funnel effect, right?
What do you mean by
either hierarchical flow, unidirectional flow?
Not yet. This is too simple right now, right? This is too simple. Remember, I said that we start with, the full-blown expansion, right? So literally you have hundreds of these Q1 squared Q2. You have Q1 Q2 squared, you have Q1 Q2 Q3, you have Q1 squared Q2 Q4, right? And you have fifth order coupling. You have this. Every one of them brings a new wrinkle, new resonance into the system. So when all of them are there, then the energy is going to sort of now have very rich dynamics in terms of how it's going to flow. So right now it's too simple, right? Just for illustrative purpose, it's just two modes. And I'm just focusing on just one coupling, just to illustrate how that one coupling actually transfers quanta between modes, essentially. And Ramsesha, you're exactly right.
If I can interrupt you one more time.
Sure.
Also to Ramsesha.
Yeah.
The resonance is important, but what is more important is this carbon dioxide. The V2 of bending does couple with V1 of the stretching, but only when the L equal to 0. L equal to 2 mode does not couple.
Correct. Absolutely.
So the Coriolis interaction and the vibrational angular momentum are important. What's more important is carbon dioxide is absolutely important. From politicians to common men should understand this, or women as well.
You know,
The
I don't know, that
global
is why-
warming happens. Global warming happens because of the bending mode of carbon dioxide.
Yeah, I don't think I can write that in a. Yeah, well, you know, maybe I can write that in a
No, seriously, Srihari, global warming happens because of the bending mode of carbon dioxide.
Okay, okay, yes.
Okay. I would sort of request everyone to wait on for the comments because it has been a little bit of an extended session. I would like to tell Srihari that Srihari, you can go as long as you want, but there is a sort of a we can take things in the next talk as well. So you can speak for uninterrupted at this point for next 5 to 10 minutes, and we'll see where we are, and then we can take more questions and discussions. I do not want to offend anyone here, but just let him finish, and then we will have the exciting round of questions and discussion.
Yeah. I think at the end we will take the questions now.
Yeah. Thank you.
Okay, good. Okay, so this is just sort of a, to just sort of show is how this one coupling term, right, starts to do this. And an important point which I make here, which is that once you have a resonant thing, for any dynamics, of course, whether you took in time domain or frequency domain, they're related to Fourier transform. So different sort of experiments is to do time domain experiments and frequency domain experiment. They do one or the other depending upon the advantage. What are you looking for? If the phenomenon is ultra fast, then time domain experiment is what you want to do. I mean, you've got better hand on. But if you're doing frequency domain experiments, you're looking at things which are happening on tens of picoseconds. And if you have the resolution, then you should do the frequency domain experiment. Right? So people like, Kevin Lehman, Scholes, Pate, I mean, they're absolute bosses of this. And that's why there's such wonderful data that I showed you before. Okay. Right. So, all right. So what can we do with this? I mean, so at the moment, what happens is this. Oops, if I can go, am I stuck? Okay. Seemingly, I cannot move forward. Can people hear me yet?
Escape.
Okay, let me stop share for a second then.
Yeah. Stop share.
You may have to reshare again.
Let me do this. Okay, let's share screen again.
Yeah.
Cool. Yeah.
There. You can see now.
Fine. Okay, good. Okay,
perfect.
So what happened? Now, this is where all the discussions that were happening before, right? They sort of already guessed what I'm going to say. And harmonicity is actually the key. Remember, I said we took harmonic oscillators and we're coupling them and saying, okay, so that's good enough to illustrate what actually happens with these couplings. But the key is when you take harmonic oscillator, as also Mangala was saying, right? Basically, in harmonic oscillator, they're great systems, but they are unfortunately too simple when it comes to vibration. Because in a harmonic oscillator, if you're resonant forever, right? Because harmonic oscillator frequencies don't change with energy. So there is no way they can detune out, okay? They cannot tune out. So basically, which means that they are forever resonant, they're sitting there, they're simply going to take heat up and then boom, not going to work. This is not good at all, okay? So nature, of course, that's why it designed vibrations to be anharmonic. That's the point. So when you take the harmonic, right? Oops, go back. Hopefully I have my annotation still on. Yes, okay. Good, okay. So if you take this now and go to an harmonic system, which I've done before, what happens essentially is that, well, the zeroth order still you have the diagonal anharmonicities. Now the nice thing is that you have only a portion which is resonant with what you have. And if you move away, the state will actually detune. So it will not be in resonance. So it's sort of, so it takes its energy because it's resonant. And then it goes up, for instance, the frequency changes. Because it's anharmonic, the frequency changes with energy. And when its frequency changes, it tunes out of this resonance. Okay. Now it has opportunity to give it to something else. Right? And that's the beauty. That's exactly how it is. So harmonic oscillator is nice to illustrate, but it's really, the resonance is too strong forever. The point that I'm trying to make is, why can't I? Seemingly, if I annotate, I have a problem. Okay, let's try this again.
Use the laser pointer, Srihari.
Yeah. Let's.
You could use the laser pointer.
Okay. So, therefore, this is the point. So the problem is anharmonic, right? So you have several things. The detuning is very, very important. The detuning actually is as important as tuning. This is the whole point, okay? And so the anharmonicity basically makes the molecule, it makes the molecule learn to let go of things. This is the reason that things are stable. But the more important point, of course, is that this brings on this very rich dynamics, okay? The whole idea is that, you have, this frequency depends now on energy, but this frequency therefore should be seen roughly as sort of a derivative of energy with respect to the quantum number essentially. And therefore, this is now going to bring in a lot of richness to this energy flow. Okay. Oops. Okay. Now it turns out there are certain simplifications because you can go back and say, well, there are all these coupling terms. If you throw all of them in there, I mean, there's going to be all these resonances. So lots of interesting things, a lot of complicated things going to happen. So are there simplifying things? So well, it turns out there is one way to simplify, and that is if you take the same. So let us take the same coupling term that we had, okay? Let's say, okay, we will do something simple here. We will retain only this part of this, okay? And it's Hermitian conjugate, of course, because we want Hermitian operators. Now, from where you are coming, this will be called as, pastime scale averaging or rotating wave approximation, whatever you want to call it. Idea is you are throwing away the sort of terms which are perturbatively cause very small effect, but you're retaining the one term that, as I showed you in the previous two slides, is going to have the strongest effect, right? That's the up and down sort of thing between two oscillators. Well, if you do this, then it turns out there is something very interesting. The Hamiltonian now actually commutes with this combination of occupation numbers. This particular combination, N1 plus 2, N2, which I've denoted by P, is actually called polyad in spectroscopy. And it turns out because it commutes with the full Hamiltonian, therefore the Hamiltonian becomes block diagonal. And the intramolecular vibration energy flow is going to happen within a specific set of states that belong to that polyad. Now, of course, you might say, well, that's very good. I mean, that simplifies, but is there any experimental reason why would you do that? Is there experimental evidence? Turns out there is. So polyads are not theoretical constructs. Molecules, as their spectra shown by dispersed fluorescence, stimulated emission pumping, show clumps of transitions, okay? And these clumps actually belong to these polyads. So it's the spectrum. Nature is telling us that, in fact, these molecules, they utilize this sort of local coupling. There's a strong coupling. This is the most important one, this polyads, and therefore, now they're not strictly considered. Of course, you have polyad breaking things too, but it's like our selection rules, right? I mean, when you say harmonic oscillator, you say delta V plus minus 1, but we know you have overtones and because there's anharmonicity. Something similar. You have polyads are very useful because they give you an additional constant of the motion, which is very nice. Okay, theoretically, they make computational easy. But more important than that, there are spectral signature, nature, actual spectra, for example, acetylene or whatever, have many of these things. They actually show that you have this approximate conserved quantity. Why nature has that itself is a fascinating question. Why weren't these transitions just sort of random graphs? Right? People were excited about saying. So, for example, in acetylene, even if you go up to 20 quanta in the bending, you can see clumps. It's not graphs, it's not random graphs, it's not this chaotic intensity distributed, fragmented over the entire range. No, it's actually organized. And then this is actually a very important pointer into the way the molecules are actually undergoing this dynamics before they react. And then so this is something very important. Of course, for a spectroscopist, this is fantastic because whenever you see patterns, it lets you classify things, it lets you assign things, it lets you tag on to particular states for further study. Okay, so the polyads. Now you say, well, this entire discussion has been with one resonance, right? Suppose you have multiple resonance, what happens? It should happen. If you have all these H0, then you would have these cubic terms and the quartic terms and the quintic, and you go on. I mean, you'll have all the infinity of terms here. And of course, different resonances are going to come in, not just this 2 to 1. You will have a 3 to 2, you will have a 3 to 4, you will have 1 to 2 to 3, right? 1 to 2 to 1. I mean, multi-mode resonances, not involving only 2 modes. I'll give you an example, maybe tomorrow. But the point is that all of these resonances are there, and you say, well, what happens then? Well, this is the interesting part. And I've sort of shown you here, hopefully you can see this. So if you have only the one term we were thinking, for example, the A1 dagger, A2 is 2 to 1. We just saw that there is a polyad, it's N1 plus 2N2, right? This is conserved. Now you might say, suppose there is another independent resonances, call it A2 dagger, A3, A3, right? That also comes because there is a third mode. Now, if both of these resonances are present, it turns out that, of course, N3, which was a good quantum number in the first case, is no longer a good quantum number. Similarly, the polyad, which was good, which commuted with the Hamiltonian, no longer commutes with the Hamiltonian. Okay? But what is interesting is that there is another polyad, you call it super polyad. It is this combination, N1 plus 2N2 plus N3. That commutes with the Hamiltonian, even when you have these two resonances. Fascinating. Very interesting. Well, is it seen in nature? Is it seen in the spectra? Yes, it is. Okay. Now we say, all right, let's add a further higher order term here, right? This is 1, 2, 3, 4, 5. This is going to come at fifth order, right? If you add that now, of course, now what happens? None of these polyads are good. None of the vibrational quantum numbers are considered good anymore. And you have a full-blown coupling already with just these three different present. And now you can imagine for a molecule like methanol, where you're going to have a slew of these terms, or for a molecule like acetylene, at excitations of 22 quanta in the bending with the kind of states and density we're seeing there, how many resonances are going to be sitting? Will that make, that means, is this direction going to obviously imply spectral complexity? That's the question. Well, depends upon who you ask. Turns out, the spectra doesn't become structureless still. And that's the first clue that the vibrational energy flow in molecules, even at very high excitation energies, because of the anharmonicities, because of just the right way that these resonances come, the dynamics is still beautiful. It's not something you cannot understand. Right. So, question is, can you actually use this? Can you use it to your advantage? Well, Ned Seibert, who gave the last talk, is actually one of the bosses in this. So the question is, how can you systematically construct Hamiltonians with relevant polyad structure? Turns out this is a technology that is known since the time of Van Vleck. Okay, so this is not something new, but if you want to really know how it is done, this is something that some of the best people in this field. So Ned Seibert, obviously, this is a classic reference, and then Marc Joyeux, who actually came to one of our STMCs, early STMCs in 2006, right? And a more recent one by Stepanov in 2013, which actually tells you for a whole bunch of molecules, okay, going from simplest to very complicated, how you can actually construct Hamiltonians, which are very powerful Hamiltonians to understand the dynamics. Well, there are generalizations. Let's not worry about this for a moment. So what I'm trying to say is that once you throw in all the couplings, so this simple sort of one-line motion that I was writing now is replaced by some sort of a diffusional motion in this lattice. It's a two-dimensional lattice. If you generalize it, it's a three-dimensional lattice, right? This is a diffusional motion. There's a constant energy surface, and this point, this way, the green, for example, bright state is going to visit or diffuse along this. This is actually the process of intramolecular vibrational energy flow in a real situation. This is what's going to happen. So there are several questions. What's the time scale? Can you calculate the rate? Can you get an expression for the thermal rate constant? Are there many pathways? Is there a dominant pathway? Can you pick that off somehow? Is there a preferred pathway? Even in a very complicated system with all these gazillion of resonances. Oh, we said this is diffusion. Well, whenever you come diffusion, you can always ask, well, is it a normal diffusion? Is it an anomalous diffusion? Is it truly diffusion? Is there a diffusion constant? Can you say that here? Remember, there is no temperature here. The temperature is 0 on top. And of course, the most important, what is quantum about? Right? So all this, you'll see that in a moment. And you say, well, where is the quantumness, right? With this coupling structure, although that's true, all these pathways, are they impossible classically? Can they happen classically if you were somehow to construct this or look at the classical dynamics? Or even if there is classical, is there above and beyond something that's quantum? There's a pathway that classical mechanics simply cannot take, but a quantum will do. It turns out that's the case. It's there. Molecules have it. Right? And the spectral signatures are there as well. Final question. Well, if you get all of these fantastic understanding about this process, it would be a shame not to control it, right? What's the point? If you have all this understanding, then how about controlling it? Well, I'll just sort of end by saying this particular sentence. IVR got a very bad rap when lasers first came. People say IVR is very fast, it's too fast, you cannot do more specific chemistry, and so on and so forth. These were statements being made in the 80s or late 70s to 80s. But what people now are realizing is that you can perhaps use energy flow not as a villain, but as a hero. Because if you know the pathway, if you know the mechanism, if there are dominant pathways, even in very complex molecules, then the IVR is going to take you to places where your laser wouldn't have taken. Let it go there, use the IVR as a friend, and now bring in a second laser to do what you want to. So, perhaps, right? So that's really the interesting part. And now I think I'll stop here because it's the right time to stop. I think it's gone almost for 2 hours. So what I will do tomorrow is to really sort of bring out this with examples, okay, and particularly address this issue of what happens when you have several resonances and how this interplay of classical and quantum pathways and energy flows happen. What is quantum about it? What is classical about it? And then sort of try to give you some insights about these questions that I just posed for you. Okay, thank you very much.
Fantastic, Srihari. Thank you very much. I just want everybody to clap once. This was a fantastic session. Probably, Srihari, you have crossed over what Ned did in terms of not only inviting people, but also sort of getting the number of questions that you had. And I'm really glad that all of you asked questions. And I apologize if I stopped you at the last point, because I just wanted him to finish and come to this slide, and then you can have a discussion again. All the discussions are exciting. So let's go ahead and ask more questions. So please unmute yourself and ask questions, or raise up your hand. And
can I ask a question?
Better,
yes, Vivek. Yes, Vivek.
Yes.
Yeah, thanks, Professor Srihari. So, I mean, I must admit, so I was completely ignorant about these polyad structures, whereas, so the background where I'm coming from is, it seems very similar to where, these polyad structures can allow you to mix two different electronic states. So now if so just to sort of pose my question, so, in that community, there is a thought that, okay, you are in a fluctuating environment. So ultimately, the existence of these mixed quantum mechanical degrees of freedom, enabled by these polyad structures, really depends on how fast is the decoherence timescales. So now, if I were to, with the same line of thinking, if I was to pose a question here, so if you see, if you excite, let's say 10 quanta into a methanol, a couple of methanol modes, let's say Q1 and Q2, and you are still able to see structured spectra, can I say that, or would it be correct to say that these modes are sort of more, they do not decohere as fast because of their interaction with the rest of the vibrational degrees of freedom? In other words, they do not play that big of a role in IVR. So that's the conflict that I'm having.
Yes. So that's one way of thinking about it. In fact, I think there is a very, so I'll put up that reference tomorrow, sure. Although I haven't read that paper, but I was a very cursory glance. So I think Albert Stolo's work very recently, where they actually, I think in the electronic state setting, energy flow, they actually bring out the polyad structure system, explicitly the polyad structure in the vibronic management. So it's very exciting. I mean, I haven't read that paper. I think it's fairly recent. I just downloaded it, so I haven't had time. I've been preparing for this talk for the last 5 days, so I haven't. But I'll put up the reference for sure tomorrow. I think it's Albert Stolo. So yes, that's one way to think about it. So you can say that if the IVR is actually restricted to a subspace, right? So in some sense, you could say that this is the protected subspace.
Okay, yeah.
Right? So if you put the system in there, I mean, the energy is going to slosh around only in that subspace, and you're guaranteed that this is over experimentally relevant time scales. It's not going to go out there into one of these other modes. So in that sense, you could say that the IVR is providing you with sort of a decoherence-free subspace.
Sure. Yeah.
Right? So indeed, yes. Yeah.
Okay.
I think Martin Grubler sort of thinks sometimes along those lines. He has used those sort of language before.
Okay.
Yeah, indeed.
Okay, yeah, I really look forward to that Albert Stolo reference.
I will do that. Tomorrow I'll put it up for sure. Yes.
Okay, thanks.
Thank you, Vivek.
Thank you, Vivek. Professor Sebastian.
Srihari, that was a beautiful talk.
Thank you. It's a great this thing coming from you.
Well, you see, let me put the question. The question is, you have actually put the question on this slide. Is it normal diffusion? I mean, why should it be normal? I would have expected that it is completely quantum diffusion, right? I mean, after all, it is quantum diffusion, and then normal diffusion. Is it a result of the complexity of the system?
Yes. So I will refer. So I'll sort of give the hint, and you might have heard me say this before. So this picture of this seeing IVR as diffusion in the quantum number space really came from the work of David Leitner, Peter Wolness, and David Logan. And it came from an analogy between Anderson localization and the phenomena of intramolecular vibration. So it turns out, and also Sarah Schofield, who was one of the original authors on that. But what is interesting was, what they were perceiving was a very large system. This quantum state space would be pretty large dimensional. And essentially, you would have so many couplings that you would have sort of, it will be broadly chaotic everywhere. Okay? So very little structure. So the idea then was that the chaos is sort of broad brushstroke of chaos. You essentially have very little correlations anymore in terms of going from point to point. So you would sort of begin to expect that when the energy flow transition is exceeded, it will be more or less like a normal diffusion, right? So that was the expectation. So, but it turns out, and you're right, even in that limit, when you kind of get to that limit, it turns out that it is not necessarily normal. You're right. So there are several reasons. So one is, of course, what you mentioned, is it's actually a quantum diffusion in some sense. On top of it, turns out even classically, sort of building up on that idea of David Logan, Peter Wolness, that it is completely chaotic. You would see this. Even classically, complete chaos actually is not black and white chaos or lack of order. There is actually lots of interesting correlation. So from both points of view, yeah, I mean, you have to push the system fairly hard to get it to normal diffusion. Yeah. You're right. Yes.
Srihari, what is
can I ask this
diffusion?
one?
Yes, Professor Sebastian. Yes, continue. Yes.
Yeah, well, you see, the other thing is I am slightly confused by the terminology, because when you say resonance, that means the two states are almost close in energy, but the existence of a polyad doesn't imply that, right?
No. So what happens is, so the polyad by construct, all the states that belong in the polyad will be near degenerate. They will not be exactly degenerate, but they will be near degenerate. So if you were to plot the energy values, for instance, right? So you will see bunching of levels. Okay? So when you have bunching of a set of levels, and so compared to this spacing between one clump of levels and the other, these are essentially degenerate. So what the polyad does, so what the resonance does is, so the zeroth order, they are perfectly degenerate, and the resonance actually comes in and breaks its degeneracy. But it breaks its degeneracy in such a way that it creates sort of a quasi-degenerate set, right? So there's a very, a clump of states, if you want, and that's the polyad. So within a polyad, they're not exactly degenerate; they're near degenerate, particularly because it's an anharmonic system, for sure.
Okay, thank you.
Yeah, thanks.
Okay, thank you. I just would like an attendee who has not asked a question, Shomin Ghosh, who would unmute yourself and ask the question, Shomin.
Yeah, and thank you, Professor Srihari, for the illuminating talk. So I'm trying to make parallels with IVR and electronic energy relaxation. Can you hear me properly?
Yeah, I can hear you. Yes.
Okay. So I'm trying to make parallel of electronic energy relaxation with IVR, and electronic energy relaxation is mediated by your vibrational modes, and there is this concept of vibronic enhancement by the resonance.
Yes.
So do you anticipate any role of this rotational coupling with these vibrational modes, and can it enhance the IVR rate or change it? Another thing is, is there any, like, so because they are coupled, is it non-local vibrational modes that are impacting the IVR?
Okay, but the last part I'm not sure. I would not venture to give an answer to that last part of whether it's a non-local vibrational mode. But one thing I can tell you is for sure you're right. So the first part which you said, indeed, so people are looking at this sort of the vibronic coupling, right, which is going to funnel energy. It is, in fact, there is a parallel, in fact, not just a parallel. I mean, you do have the coupling of these electronic states along with the vibrational manifolds, which is going to mediate the idea. So the picture that will come out, whether you're looking adiabatically or diabatically, it depends. But adiabatically, you have the upper state when the system is in the upper state, it is undergoing some IVR, and then it goes through this conical intersection. If there is a conical intersection, that's usually ultra fast, right? And then it comes to the ground state, and then it will have an IVR that's going on to cool in the ground state as well. If it cools, that is, it might not cool very efficiently. Depends on the extent of it. So you're right. I mean, there is definitely a parallel for sure. And as I was telling Vivek as well, so the Stolo's work, and there are other works as well, where this vibronic, how do you modulate the vibronic couplings in order to now exploit this energy flow pathways? This is a fairly active, people are thinking fairly actively about this. Yes.
I see. Thank you.
Thank you. Thank you. Professor Ram Shesha.
Yeah, okay. Very nice talk, Srihari. I enjoyed it. See, I have just two comments. One is that it's the approach and other things are somewhat similar to what one finds in, for example, intermolecular electronic processes like singlet fission or electron hole recombination and other things.
Mm-hmm.
So it's in a way somewhat similar is what I found. The second one is about the Anderson localization that you were talking about. The Anderson localization is basically because of the diagonal disorder.
Yeah.
But here what I'm saying is the interactions are mainly off diagonal.
Yes, sir. Absolutely.
So whereas
yes, go ahead.
You don't have a localization because of the off diagonal disorder in materials. For example, mercury is a metal.
Yeah.
Okay.
You know, you're absolutely right. In fact, to put it sort of cryptically to others, but probably very clearly to you, this is in fact an example of many body localization.
Yeah. Okay.
So this is actually an interacting Anderson model, truly. So the energy flow problem is actually an interacting problem. Absolutely.
Yeah.
Indeed.
Okay. That's all. Thank you.
Thank you, Professor Ramshesha, for coming in. Thank you. I just wanted to mention Jarlai is also here. He has joined in, and also
sorry, JD, Ravi Kishore has hand
and
up.
Ravi Kishore has a question. Yes, I'm coming to that. Ravi Kishore, could you unmute yourself? Yeah.
So if you want to pitch in rotational coupling, will it be like equally important, or how do you pitch in?
So there are systems for which the rotational coupling, particularly that will involve Coriolis effects, are extremely important, right?
Okay.
Now, if you actually go down to eigenstate resolved spectrum, right, they are actually built on rotational scientific. I mean, so some of these fine lines that I was showing you before actually built upon sitting on rotational transitions, very specific. And there are all sorts of effects are there which have to do with rotation. So there are systems where it is absolutely important, right? But by and large, what is now known for some of the examples that I am showing, for example, is that the rotations add in an effect. In cases they can become sort of very interesting, but the vibrational coupling dominates, at least the early time dynamics for sure. Okay, longer time dynamics, the Coriolis coupling, these things can actually take over and sort of fragment this intensity over many other states. And this does happen. This absolutely yes.
Or is it possible that you could have it other way around?
You mean the rotation dominates vibration?
Yeah. Maybe there are systems.
Well, you know, I would be hard pressed to find such an example where the rotation outscores vibrations in terms, right? Because the problem is this, see, if you go back to the original Wilson, Howard, Watson, Hamiltonian, right, when you write things, so the vibrations and rotations are sort of intertwined. I mean, they are there together.
Yeah, sure.
So in some sense, you cannot have one without the other. You can say that, right? But if you look at this expansion, you simplify the Hamiltonian or do what is called this canonical, you transform this Hamiltonian using contact transformation, so on and so forth. What you find is you have terms order by order and with sort of relevant, relevant strengths and couplings. And it turns out, so for example, if you look at a textbook, more detailed textbook like Califano, vibrational spectroscopy, okay, or something like that, you'll see these terms being written very explicitly. And what you'll see there is that you can estimate for sort of typical frequencies, vibrational frequencies and rotational constants, what these coupling strengths will be. So unless, as I said, unless there's a very special case, for example, in acetylene, you saw that at high, you saw this counter-rotating mode. It looked exactly like rotational angular momentum. In fact, it is rotational. So when people model acetylene, because there are degenerate bending modes there, you do have rotational angular momentum that is taken into account. The vibrational angular momentum is taken into account in acetylene Hamiltonian. So those kinds of systems, you would have to build that in. You cannot neglect them because they're really important. Yeah? So that will definitely come in.
So what do you think is a driving force for such a thing? Is there a driving force or for this flow of energy?
The driving force is these couplings that nature has given for each molecule, right?
Because you have back and you can also have energy flow back and forth, right?
Oh, yeah. There is a back and forth. It is, so as I said, the simplest assumption is saying once the energy leaves a state, the mode, it never comes back, right? That's the simplest thing to say. But actually, it turns out even in molecules which are large, sufficient density of states and so on and so forth, you can, in some limit, over a very long enough time, you will see an irreversible flow. But on experimentally interesting time scales, you will see it sloshing back and forth between states. And it can actually get locked between states also in very interesting ways. So I mean, so there's a whole gamut of phenomena depending upon the system that you pick up or the mode that you plug using it.
Sure. And one more thing is it correct to call it quantum diffusion? I think one of the when it's a quantum, it's because the energy levels are of course quantized and things like that. But I'm just curious if the terminology.
It's a bit. I mean, it's a bit of a loose-handed terminology. What Logan and Bollness were prompted by was that extremely large state space. So they were really thinking of the limits where you had hundreds and thousands of vibration modes, right? So the dimensional, I'm showing a simple three-dimensional thing on the screen right now. It's a really doesn't do justice to Logan and Bollness what they had in mind. They really had almost in the macroscopic limit. That's what they were thinking, right? So there, what happens is, basically the energy level spacing, right? I mean, the effective Planck constant is essentially low. And the level space, the density of states is so high that the level space, if you find a level, I mean, you're almost guaranteed to find another level within a mean level space. So it's really dense packed, right?
Yeah.
So basically, imagine this in a large dimension space, you will have this lattice, it's almost like a continuum.
Okay.
So there, in that limit, you can think of it as a sort of a diffusion, right? In that sense. So that is the idea. I mean, in any case, there is nothing which prevents you from, if I can, let's see if my annotate will let me do this. So there is nothing that prevents you, for example, if you take a initial state, right? And there is nothing that prevents you from quantum mechanically looking at this object.
We are not seeing anything. Okay, now you are seeing. Yes.
Yeah, this is slightly.
Yeah, we can see. Yeah, we can see.
So you start with some initial point in quantum number space. You can look at his time evolution, and then you can do the usual thing you will do in StatMech to do this. And you can ask this question: well, how does this scale as a function of time? Right? What power of alpha are you talking about? I mean, there's nothing that prevents you from not doing it. You can do this, right? You take a particular initial state and do this. Yeah.
That's the time evolution.
Sorry?
Time evolution.
Yeah. So you have this initial state, right? It's right here. And as it's evolving, right? It's basically this evolution. You can ask, right?
Yeah.
How is this evolving? Where is it going? And then you can average, you can do a quantum mechanical average, right? Which is the usual thing in the state that you pick. You do the quantum mechanical average, you can ask, how does it vary with T, right? How does this evolution go with T? I mean, presumably if it goes linearly with T.
Yeah, I think JD, we can stop now.
Yeah.
Sanjay, I think.
Sanjay has one question. I think we'll stop after Sanjay.
Hi, Srihari. I mean, it's always a pleasure to listen to you. There's just one question I had. Some point somebody asked you the carbon atoms, at where do you stop, etc., etc. The energy flow. It just occurred to me, is it like in NMR, there is a through space coupling versus through bond coupling. Likewise, in the guitar strings, you can see if the two strings are tuned very perfectly. You can see the resonant transfer. So, is there a way to get this factored into this IVR thing? Does it happen? The two modes are very far apart from each other, but having a resonant frequencies. Would that?
So by far apart, you mean so in spatially?
Molecularly, they're say distant from each other, like C10 or something.
Yes. So in fact, there is no classical pathway, but you can have something like the analog of super exchange. So you can have vibrational super exchange. So what will happen is that, and in fact, that is what is nothing but a quantum pathway called dynamical tunneling. That's what is happening. Right? So basically, you have this separated. So the way that it talks is that it's going to talk to the, it'll be intermediate higher energy states which will talk to this, and it will cascade over and then finally, talk to this other mode over here. Right? But then the question is that what is the time scale for that? Right? So that time scale can get pretty large if the conditions are not just right. So whether suppose that time scale is already several nanoseconds, then you're not going to catch it, or it won't be the dominant contributor to the overall rate. That's the point.
So in your tier system, that you have tier 1, tier 2, tier 3, etc.
Right.
Is that the direct coupling of the oscillators? Does that matter? Like, for example, the atoms which are linked to each other through the bonds, it is physically intuitive thing that the energy can flow from one mode to the other because of the normal modes involve the movement of all the atoms involved, which are linked together, right? So does that come into play when you have design the tier system, or it's all figured into your coupling matrix elements?
Yes. So that's right. Yeah. So the way you design a measure, and I'll show that tomorrow. So the way you design that measure, which is going to tell you when will I put a particular dark state in tier 1 or tier 2 or tier 3. So there is a sort of a, if you want a scoring function or penalty function, right? I mean, this is a perturbative estimate that is based on a particular coupling, harmonic coupling, okay, and the energy spacing between the two states that you're coupling, right? So the ratio. So usual perturbative sort of criteria, but people have sort of come up with different ways of thinking about this and different expressions, but essentially it's based on this sort of an idea. So that's right. So there is a locality to this criteria by which you put the states into, like, the first tier or the second tier or the third tier. There are also people like Martin Quark, for example. They've actually done this where the tiers are now the sort of the states in a given polyad. So you organize this by polyads now, right? And so it goes into one polyad and then it goes into the second polyad, because strictly speaking, the polyads are not exact, right? So you will have intra-polyad mixing, inter-polyad mixing as well. That's going to happen. So people have used sort of different coordinates, if you want, to tier this. And so each one gives you a different insight, if you want. But collectively, the point is that the one-dimensional coordinate is not necessarily sufficient to capture the entire complexity. And in partly, that's why this sort of thinking of IVR as sort of diffusing in this quantum number space really was very powerful, because it sort of immediately connects to the experimentalist, the way they would prepare. So for example, if you were to prepare a high overtone state, right? I mean, you would call this as a high overtone state, right? This is all the excitation is in mode N, mode 3, for instance. Whereas something like this, right, somewhere over here, this is a combination state, right? For example, it's 4 quanta of the bend and 1 quanta of a CH stretch, for instance, or something more complicated. So there was this visual way of thinking about how a light, a laser would actually sort of access this particular bright states, which typically tend to be overtone states, more or less. And so it turns out that in some way, the tiering, that one coordinate tiering sort of thing that had been there, it sort of opens up when you look at it, the quantum number space now, because really now you have a different tiering coordinate, if you want, which has to do with a distance that is defined between two states in this. And now it becomes a very rich and multidimensional. So it's almost like taking a tier coordinate and literally sort of unfurling it to see the entire process that's happening.
Okay.
Okay, thank you.
Thank you. Thank you, Srihari.
So
Thank you very much.
Bob Field had done a lot of work on the SCP triads, I think, right?
Yes.
So is that related to the IVR work, or are you just looking at it spectroscopically?
No. So he definitely used the SCP extensively to look at the acetylene spectrum, for sure, right?
Yeah, okay.
I mean, SCP was the method of choice for Bob Field for the acetylene spectrum. Yeah, I mean, acetylene has yielded a lot of its secret using a combination of SCP and dispersed fluorescence, and now I think some Stark level spectroscopy also going.
Okay. Wonderful talk, Mr.
Thank you.
Thank you, Sanjay. Thank you for the discussions and questions. It was actually continuous questioning, and there was a lot of interruption to Srihari's own IVR of giving us this talk and connecting it to so many people. So Srihari, thank you. We will continue this particular section tomorrow. Again, we'll pick it up from here. Okay. And I really could not take one student question from Krishna Priya. We will start with that tomorrow. Sure. At the very start, and go from there, because I think that will be a continuation. So we will pick up our loose ends again at 5 tomorrow, and sort of we'll continue again for a session, for entire 2-hour session that we have. Thanks, Srihari. Satish? Yeah.
Thank you very much. Thank you.
Yeah, it was fantastic. Debanu also came. Debanu, one of your old students.
I saw it. Yes. Yeah, wonderful to see. Yes.
Okay,
good.
Yeah.
Okay, see you tomorrow. Bye-bye.
Yeah. A lot of faculty members from across India have joined. Yeah. Nishant Nair, and yeah. So thank you all for coming in.
Yeah, thank you. Bye-bye.
Thanks, Srihari. Yeah. Okay.
Bye, Srihari.
Okay,
bye. Bye.
Thank you.